Welcome back. In the previous section, we looked at a historical take on a residential PV-only system from 2009 with high SRECs, no time value of money considerations, and some local rebates that were in effect. In this next section, we want to look at a more typical current use case for a commercial, relatively large-scale hybrid system with both PV and battery energy storage. To do that, we're first going to close this tool, don't save, and open up a fresh copy with the default inputs. So here we are. This copy opened up to the PV in tab, which is fine. We know that the intro instructions are still there, and we're going to start using the default values for the PV system generally throughout this example. Now, a point of note is that the values that are in the tool when you download it from us are not necessarily suggestions of correct values. They're merely suggestions for what magnitude you should be in. For example, it's useful to help understand the units. This value of the retail cost of electricity is in fractions of a dollar, so it's cents per kilowatt hour. If you tried to put in $2 here, you'd know that that's not really anywhere near the default value, so it's probably unlikely. Similarly, for the cost of a system, you see $1.40 in here. You know you wouldn't put in $55,000 as your base cost because that's totally out of the realm of the default value, which is clearly a dollars per watt unit. So as I mentioned, we're going to look at a commercial hybrid system for this year. We're going to use the retail rate of electricity that's in here, no escalation value. It's going to be a corporate system, so a rough average corporate tax rate of 21%. We have a discount rate, reinvestment rate included. SRECs are pretty low. We're going to leave the PV inverter size at the default value. However, we are going to change multi-port inverter to yes. Now what this does is it makes this next section active, which has some D-rate values for the battery system. Typically, battery hybrid inverters had slightly lower efficiency. So for example, a typical grid-tied PV inverter was running at 96% efficiency, where a hybrid inverter, due to the multiple conversions, if you're running your PV through your battery always, like a double conversion UPS system, there's a little bit of an efficiency loss there. So some of those inverters are, 85, 89, 91% efficient. We're going to kind of split the difference here and say instead of 96% like a grid-tied inverter, we're going to drop that down another 3% to 93% efficiency. Critical hours during peak sun and utility call hours, we're just going to leave as the default values here for this case. Base capacity factor, we're saying this is a pretty much optimally sited system, good tilt, appropriate azimuth, 1300 kilowatt hours per kilowatt per year. We're going to leave the system pricing in here, default values as well. It's a fairly large system, so there's probably some economies of scale. It's bought with a battery system, so the price is probably driven down pretty low. We'll have $1.40 in here right now, which is a pretty reasonable price. No inverter replacement because that's going to be covered on the battery page because this is a multi-port inverter, and no financing either. A point of note is that the financing on the PV sheet is independent of the financing on the battery sheet. So if you wanted to finance your system entirely, you would do 100% on both input sheets. We move over to tax implications. It's a commercial system. They are probably writing off their electricity expense. So we're going to have that on. Depreciation, active, bonus depreciation, yes. No local rebate, that's been taken out. and they are capturing the federal ITC. Let's bump the period of analysis back to 10 years and only really focus on the first 10 years of the system for this analysis. So the next step would be, after we have everything configured on the PV in sheet appropriately, we would go to the battery in sheet. I'm going to zoom in one more notch. When you get to the battery in sheet, you see the market section is grayed out and purple text, meaning those values come from another sheet and they've been already entered, and in this case they're coming from the PV sheet. The next big section that's unique for the battery system is the revenue streams. We have currently a multitude of potential revenue streams available, but for this analysis and in our first pass, let's simplify it a little bit. Let's assume that they are primarily focused on the real-time market, which in Pennsylvania for us is the Reg D ancillary services market, sometimes commonly referred to as fast frequency response. And the average dollar per megawatt hour of participation, based on some historical number analysis, right now is about $16. That value is constantly changing, and instantaneous values in the real-time market go anywhere from $0 to hundreds of dollars. But the average right now, and what this input is concerned with, we're going to use $16. We're not going to touch the mileage payment for now. That's a little bit more of an advanced use. And participation in the real-time market is going to be 100% of inverter power. We want to dedicate as much as we can of this resource into that market. The daily capacity turnover value has to do with how many kilowatt hours are being pulled off your battery and put back into your battery as it's breathing and cycling, charging and discharging, functioning in the real-time market. You're able to get a greater than 100% capacity because you're having small incremental discharges followed by recharges. So for 280%, in a very simplistic manner, let's say you have 100%, well, no, that's too big. Let's say you have a 50% discharge, then you have a 50% recharge. So that's 50% capacity. It does it again. Now you're at 100. It does it again, 150, 200, 250, and then you say you have another 30% discharge and a 30% recharge. If you added those all up, you'd get 280% turnover for that day. This value is calculated based on the market signal, and right now we found that that's a fairly reasonable default value to use. Sync reserve, let's just zero that out. And as we do that, I'm going to pull over this chart and shrink it. Sorry for the jumping around. Zoom back in. I'm going to bring it right here so that we can kind of see the effect of these changes as we move along. So this chart represents the revenue stack. And as we get rid of the sync reserve, it's currently at $92 per megawatt hour. If we get rid of it, sorry, I want to stretch this just a little bit. There we go. When we get rid of it, we notice the sync reserve falls out of the revenue stack. So if I hit Control Z to undo it, you'll see a dark blue line appear, and that is this sync reserve as part of the revenue stack. So if we get rid of it, once again, you see that line disappears. Now, the usage of the battery capacity is still calculated. So what we need to do is get rid of the hours per year, and you'll see the revenue stack grows a little bit. And that's because it's pulling those sync reserve kilowatt hours out of the calculation and allowing the real-time market to utilize that capacity. Same thing for call hours. This would be a situation where a utility has an issue and they need additional quick capacity. They could discharge your battery. Let's get rid of that as well. And you see that disappear. We're going to get rid of the contract as well. So the revenue stack grows back, and we'll get rid of the usage per year. Load shift energy. Similar. Let's just get rid of it for a simple calculation. This would have to do with if you're trying to shift early evening, late afternoon, peak, you may be shifting some energy usage back and forth. Right now we have it showing 50 kilowatt hours per day. And the delta value, we'll talk about that in a future detailed video. So let's just get rid of it for now. Peak shaving. We've got two options for peak shaving. There's the demand reduction type of peak shaving and the capacity reduction type of peak shaving. The demand reduction type of peak shaving has to do with limiting your daily average peak. So if every afternoon your facility has a big peak and then all of a sudden it needs 50 kilowatts, you're going to be charged for that. Maybe your battery is going to be used to reduce that by 15 kilowatts. Now, because you have to shave that peak every single day, you may need to do that 260 times per year, which would be, I believe, basically the weekdays and not your weekends. So let's just pull that out of here for now. 0, 0, 0. Peak shaving capacity reduction. This has to do with your coincident peaks, what your demand is at the specific time where the utility grid and the RTO says this is our peak time. How much can you reduce? That's an easier number to reduce, so you can get a larger value and you don't have to do it as many times per year. But for the sake of argument, once again, we're just going to zero that out. These next two revenue streams, peer-to-peer contracts, standard and premium, have to do with the future capability and possibility of selling an electrically connected neighbor energy. For the purposes of this exercise right now, we'll come back and revisit it. We're going to zero those out also. Now, as you see, the revenue stack starts to shrink dramatically. Maybe not shrink, but there's definitely fewer sections. The top section, the bright green right now, is SRECs. And you can see what these sections are instead of using the color key, simply by hovering over them. The blue section is the real-time market revenue, and the slightly darker green section is your avoided cost of electricity savings. Down below, you see all the expenses, such as your CSP services, an inverter replacement or battery replacements, writing off electricity expense, etc. Now that we have the revenue streams relatively simplified and an understanding of how that affects this revenue stacks chart, let's bring this out of the way a little bit and come down and look at the physical and the cost structure of the battery system. We have a 500 kilowatt PV system, so it's multi-port as well, so it really only makes sense to have your inverter size on your battery system, which is now both for the battery and the PV, to at least match. If you didn't have enough inverter capacity on your battery with a multi-port inverter, you wouldn't be able to utilize your whole PV system. So we want to at least match what's on the PV input page. And then the battery capacity is the kilowatt hours of energy that the battery contains. So you could have a situation where you had a larger battery size. For instance, maybe we have a 1 megawatt battery. So this situation would say potentially that you're not ever going to run at a 1C rate. And we'll cover that in detail later. But this situation right here is saying it would take 2 hours to fully discharge your battery because your inverter is only capable of pulling 500 kilowatt hours off per hour. You could also have a situation where you had a significantly larger battery. Let's do 5 megs right now. And what happens here is you get an alarm. So as we mentioned, this system is not, or HybridFAST is not really a design tool per se, but there's situations where we do try to protect the outputs, if you will, just to let you know, hey, something may not be right here. there are still some constraints that you need to follow, or else your calculations are really just not going to make sense. And this is an instance of that. What's happening here is your inverter is too small to utilize the full capacity turnover that's being requested up here. So for instance, this is saying you need to turn over 280% of 5 megawatts. That's going to be 14 megawatts of energy that your system needs to turn over, and 500 kilowatt inverter simply can't do that in a 24-hour period. So you get the alarm. So let's bring that back down to 500. We won't go over the C rate. We're just going to use a lithium battery for now. And let's talk about the battery charge from renewables, because this becomes pretty important for the tax considerations. If you take a look over here, the ITC is currently only showing 26%. And that's because the ITC on a battery system is directly related to how much energy is received from a renewable source to charge your batteries. If you went to 100%, you'd get the full ITC value. If you went to 74%, you'd get no ITC. 75%, of course, being where it kicks in. So if we scroll up a little bit and we look at the payback, as well as the return on investment and the internal rates of return, what you're going to notice is utilizing different percentages of charge from renewable changes your return. Let's take a look at 0 and see what happens. Well, at a 0%, your battery system in this model is not currently paying back. And that's because due to efficiency losses and the revenues that are currently included, right now only being the real-time market, the electricity you have to buy from the grid is going to kind of outpace the revenues that are available from the system. However, if you change your battery charge from renewables up to 75%, the two systems start to work together, where instead of having to buy electricity at the grid rate, your PV system is recharging the battery as much as it can, or whatever is requested, in this case 75%, and the two systems combine to help each other out. So now we have a 9.67 year payback on the battery and a 6-year payback on the PV. If we do 100% charge from renewables, we'll watch these values as I hit enter, it pays off faster. However, as you saw, instead of 6 years, now the PV system is paying back a little bit slower because it's not able to offset electricity directly. It's being used to recharge the battery. The next item is base uptime. We're going to leave it at 98%, assuming that the system is only down for like 7 days a year. Critical mode hours, we can just get that out of here. That would be a situation where if you had a facility that had critical operations, like a machining operation where if you lost power, something would be damaged, or you can't afford to lose power during some type of shutdown operation. So this would allow you to tell your battery system, prioritize resiliency and uptime, and pull yourself out of the other markets that may be taking a requirement of battery capacity. So by including critical mode hours, you're actually reducing other revenue streams. So in this instance, we're just going to get rid of critical mode hours if we're not using it. Depth of discharge, this is how much of your battery capacity you're allowed to utilize at a single shot effectively. So if you had a 1 megawatt battery with a 75% maximum depth of discharge, you would only be able to actually in one use utilize 750 kilowatt hours of battery capacity. And this becomes important because if you had a situation with maybe a lead acid battery and you're only allowed to kind of take off the top, you may run into situations where, oh, well, you're not allowed to do that based on your revenue streams, or the calculator is trying to utilize revenue streams where now you're not able to discharge deep enough. So that once again creates another battery alarm. As we move down to the pricing method, we're going to leave this pretty much as is for the purposes of this video. One point of note is that we have independent inverter costs and battery costs, and that's because sometimes people sell them separately, and also this inverter cost in a multi-port inverter pulled out of the PV inverter cost because they're sharing. So if we go back to the PV in tab, you'll see the base cost per watt is $1.40, but we're pulling out that inverter cost of 16 cents because it's used in the battery inverter. We don't have a battery inverter replacement shown. We do have O&M and insurance costs. Oh, sorry, I want to step back and say if you're trying to analyze a proposal or you're trying to create a pro forma and you know that the battery system as kind of a turnkey system is $1 per watt, say, you can just highlight these two and see how far off you are. So we would know we would need to add 6 cents to either the inverter or the battery to get to a net $1 per watt value. I do want to touch on the CSP fees here. CSP is short for Curtailment Services Provider. In order for your battery to function in many of the revenue streams, you need to have some type of control system to follow the signals that are coming from either the utility or the transmission authority, or in advanced use cases, maybe from your neighbor. Most customers are not going to be doing that themselves. They're going to be paying a third party, and that's where the CSP fees come in. So a curtailment service provider may charge you, $350 or $1,500 or $10,000 to set up their equipment and their system on a one-time basis. They may not. They may just include that. They may also charge you a monthly fee. Say it's $350 as a subscription fee for their service. You could enter it there. You could get rid of that back to zero, because what we're showing here is a very likely situation where the interest of the curtailment service provider is directly aligned with the customer's best interest. And that's done by a revenue share, or the CSP being paid a percent of the revenue that their services are able to generate you. So if you get $100 an hour from the real-time market that they're managing, you get 80 and they get $20 based on whatever percentage you put in as the revenue share. Next, I'd like to take a little bit closer look again at the revenue stack. To do that, I'm going to bring this chart back into view. Right about there. Maybe stretch it a little bit further. We understand now that the x-axis is years 0 through 10. So we're going to kind of get that out of the way just so that we can see this as large as possible. Bring that up there. So let's take a look at what happens with a peer-to-peer contract situation. So in this situation, you may have a neighbor that's connected to the same utility feeder, or a circular feeder in your campus, and you want to be able to provide them kilowatt hours. The regulatory structure, of course, doesn't quite exist for that yet, but we still want to be able to model it because we think this conversation is important. This is where the battery industry is more than likely going. So the energy that comes from your battery could be considered green energy. It could have significantly stronger resiliency opportunities. You could provide them backup power. You could do all sorts of different things with your battery through shared electric lines. Because of that, we think you can probably charge a little bit of a premium. Right now, we have the customer of this, the owner of this system, paying for 13.2 cents per kilowatt hour for grid electricity. It's probably a reasonable assumption that their neighbor is paying a very similar fee. So let's just add a little bit of a premium. Let's say we want to charge 15 cents for resilient green energy that's been charged from renewables, at least 75% right now, maybe 85%. And let's figure out how many kilowatt hours we need to sell them on an annual basis to make a difference. 15 cents per kilowatt hour isn't a lot. So let's say we were only selling them 500 kilowatt hours per year. Almost no change. There is, I don't know if it's even visible to you, but you can see it just slowly started to peak in there. So it basically makes no difference. And if we watch our batteries return on investment and payback, if we zero that out, 12.2, it makes no difference in a year payback and no difference in the ROI because 500 kilowatt hours is basically nothing. Well, our battery's pretty big. Let's try 5 megawatt hours. 5 megawatt hours, you do see it start to creep in, and it changed these values slightly. So at 15 cents, 5 megawatt hours does have an effect on this battery. I'm going to hit Control Z to undo that, and we'll watch the return on investment and the payback if we zero this out. So 0 and enter, 7.67, 12.2. So that revenue opportunity does increase your ability to have your system pay back. Now let's see what happens if we charge them less. Maybe we're only charging them 12 cents for 5 megawatt hours per year. That actually has a negative effect because what's happening here is, yes, you do have that showing up in your revenue stack, but it's taken away from your other revenue generating opportunities because charging 12 cents per kilowatt hour just doesn't make sense. That energy is better used to offset your own electricity bill. So let's put that back at 15 cents for 5 megawatt hours. Now this standard contract is kind of your basic, we'll sell you electricity when we have it. Now what happens if they have a critical need or the utility grid is down and they need to keep their equipment running, if they're a data center or a machine shop or some type of manufacturing with critical operations? Well, in that use case, you have the ability to charge a premium. And let's take a look at that next. The question then becomes, well, how much of a premium are we going to charge? Well, it's got to be more than 15 cents per kilowatt hour, which you're charging for your standard contract, and it's certainly more than the retail cost of electricity they're likely paying. Now, is paying double, triple, quadruple, or any other multiple of the retail cost of electricity reasonable? Yeah, it probably is, especially if this is really truly a premium service and they really need it. It's not price gouging necessarily. There is a value associated with being able to have electricity when the grid is not able to supply it for certain critical situations. So let's just throw in a value of 50 cents for now and see what happens. No change yet because no kilowatt hours have been shifted or sold. So when we put in, let's say, 500 kilowatt hours per year, this is a rare occurrence. Let's see what happens. Right now, the ROI is 13% with 7.5 year payback. When we put 500 kilowatt hours in, we go to 13.4. So there is a slight bump in ROI, but no change in payback because the change is so small. And as you'll notice over here on the revenue stack bar chart, it creeps in, but it's not even noticeable. Well, let's see what happens if we go to 5 megawatts, or 5 megawatt hours, excuse me. Now you can see the revenue really starting to become apparent, if nothing else, maybe not significant just yet. And once again, we've had an increase in ROI and a decrease in payback. Now, what happens if this happens all the time and they need 10 megawatt hours per year? Well, once again, it starts to dramatically be beneficial to your payback and to your investment's return. Now, what's interesting about what's going on here is, let me set this back to 500 and we'll watch this chart over here. So PV electricity savings is still a thing. It's a large portion of your return. But as we start to increase the energy we are selling to our neighbor, let's put in something ridiculous, 50 megawatt hours. You can see the PV energy that is avoided cost and a savings to you starts to decrease, and it's replaced with the peer-to-peer premium contract, but at a greater magnitude, because 50 cents is definitely worth more than 13.2 cents. Now what's happening here is there's a bit of a unique phenomenon where the system, because there's really no other usages for the batteries accounted for besides the real-time market, and you have a lithium battery with a 1C rate, you are just pushing your inverter back and forth as hard as it can. The maximum capacity turnover per year is 1.6 gigawatts. So we're able to put these numbers really high. We can put this to 500 megawatt hours again. That totally swamps the PV savings, and now this electricity write-off and purchase starts to grow. So let's add another zero here. Oh, that's now we've gone too far. You can't even push your inverter that hard. But you've effectively become an energy broker. You're buying from the grid and selling out at a premium. That would never happen, and I wanted to illustrate that there are some alarms in here. So let's pull this back a little bit, Control Z, and assume and take a quick look at what happens if you do have some internal self-consumption usages for your battery. Let's take, for instance, a load shift where we're saving 5 cents per kilowatt hour with the shift, and we are shifting just 50 kilowatt hours a day. Well, that's well within the ability of your inverter and your battery capacity to handle. But let's say you need to do 150 kilowatt hours per day. That's also capable of being handled. But now as you start to increase these, we can't get anywhere near 50 megawatts. So we can do 10 megawatts of it. Let's try a combined 20. So we'll make this 15 megawatts. Oh, that's still okay. Let's bring this up to 250. And bring this up to 10. Right now I'm basically guessing and checking to see when you exceed your capacity. 500. There we go. Now we've reached a condition where we can't operate our battery under these scenarios. So this is a good opportunity to begin exploring how the revenue stacks can interplay with each other. And it's not a super detailed engineering feasibility study for the energy flows, but there are considerations in the backgrounds of these calculations where if you're trying to push your battery or your inverter too hard, it's simply going to tell you, I'm not sure that's possible. So we can set some of these back to more reasonable numbers. And as you would include peak shaving opportunities, whether it's demand reduction or capacity reduction, that would further start to decrease your ability to participate in some of the other revenue streams like peer-to-peer standard contract or premium services. So I hope this was a useful introduction to this use case of using HybridFAST to build a PV system and a battery system and look at their combined benefits together and begin to understand how all the different revenue stacks are going to play into the equation and illustrate what the output charts are showing you. If you have any questions or comments, we'd love to hear them. Feel free to reach out to us at contact@protogenenergy.com. And once again, please just remember to put HybridFAST in the comments or in the subject line. If you have any suggestions for future videos, or we get a lot of the same questions, we'll probably put a video together instead of answering individually. But like I said, I hope this was useful. Good luck making your own scenarios, and if you have any questions, don't be afraid to reach out. Thank you.